Good morning. I'm Anil Bajaj, and welcome to this celebration of faculty careers. On behalf of the college, really, I welcome you all here. This is a program started by the College of Engineering to look at and give us an opportunity to have a conversation with our senior faculty at the College of Engineering and those who are already in many ways distinguished. They have gone through the ranks, they have been promoted here, they have tenure, they are full professors, they don't have to worry about anything in some way. Okay, today, so as you may have seen some of the announcements that are coming out, the hope or the expectation is that somewhere of the order of 20 to 25 faculty members every year are going to be showcasing their accomplishments and so on, and we will be learning from them what they did in their career, what their paths were, and how did they do it, and so forth. And maybe some of us will make them role models for us. So today it is my distinct honor and pleasure to really talk for 3 minutes about my distinguished colleague here, Professor Bob Lucht. So I have some cheat sheets here so that I don't make any mistakes. Bob is really a Purdue product, and really we are delighted that a Purdue Engineering alum is doing so well. Not that that's not expected, or unexpected, right? So Bob did his bachelor's degree in the building across in nuclear engineering in 1977, and then he did his MS and PhD in mechanical engineering and graduated in 1981 with a PhD around the time that I was coming in as a faculty member. He worked for a couple of years as a postdoc here, and then went on to the Sandia National Lab and worked there for many years till 1992 when he was at that time manager of Diagnostics Research Department. And then he joined UIUC Urbana-Champaign as a faculty member. And in 1998 he went to Texas A&M as a G. Paul Pepper Professor of Mechanical Engineering. In 2002, we were lucky enough to grab him from there and bring him to Purdue. And so in 2002, he came here as a faculty member, and in the School of Mechanical Engineering, and in 2007 he was named the Ralph and Betty Bailey Professor of Combustion and Mechanical Engineering. Right? Now, of course, that's just the official titles of the jobs that Bob has held, and we hope that he continues at Purdue for the next 100 years in all positive ways. And the way he is going, certainly it looks like our dreams and wishes will be fulfilled. Bob's research area focus, I think all of you know much better than I know, because I can't even spell what is this Coherent anti-stokes Raman spectroscopy. I don't know what it means, all right? So that's what underlies lots of what Bob does. In a more simplistic language, as I understand, his research interests are focused on laser diagnostics, developing advanced laser diagnostic techniques for gas phase media such as flames and reacting flows. The other is diode laser-based sensors development. The applications are significant in gas turbines and IC engines, and in material processing and synthesis, and some fluid mechanics and heat transfer processes, and so forth. So instead of me talking, I would rather have Bob talk about whatever he has prepared, laser diagnostics in flames, non-intrusive probes for a hostile and challenging environment. Bob, please.
Yeah, thanks for that introduction, Emil. Yeah, actually it was in 2002, Jay Gore called me up at Texas A&M and asked me if I knew of anybody who might be interested in a position at Purdue, and at that time I was not really happy there, so I said, maybe me. So here's the outline of the presentation. I'd like to talk about how I started using lasers for measurements in flames back when I was a graduate student here. And I started using lasers for probing combustion systems in 1979. And so I wanted to compare and contrast, what we thought we were doing then with what we think we're doing now. And then I wanted to talk about two subjects among many. Femtosecond CARS, which is a diagnostic that we're developing. It's what I call an advanced diagnostic that's not quite ready for application in practical combustion systems. And then I'll talk about some of the things we're doing in very close to practical combustion systems out at the Zucrow laboratories. And a lot of the things we're doing now have been enabled by the rise of high repetition rate laser technology in the last 10 years especially. And then I'll talk just a little bit, if I have time, about future prospects for laser diagnostics and combustion. So the way I got started was I was an undergrad and graduate student in nuclear engineering, and I did a summer undergraduate research project, and that mostly was on heat transfer, and I decided I wanted to do something else for graduate school. And Norm Lorendo had been my instructor for thermodynamics too, and he was very organized and a good teacher, so I approached him and to see if he had anything interesting to do. And so I did an undergraduate project on absorption spectroscopy of molecular radicals in flames, and that's a Purdue report, and that actually, it's not an archival journal, but that actually got me fairly well known in the combustion community. And it was just at the time when people were starting to think about using lasers to measure properties of flames. And when I say properties, I mean temperature and species concentration and also velocity. So we were talking about graduate school, and I started working for Norm Lorendo and Don Sweeney. Norm is deceased. He died a couple of years ago. He got acute leukemia. Don Sweeney is now at Lawrence Livermore. And at the time, they were young assistant professors. And so they had a proposal into the Department of Energy, Office of Basic Energy Sciences, to buy a laser, which was funded. And they had proposed to purchase a chromatic flash lamp pumped dye laser. Which you've probably never heard of because this company went out of business in like 1981. The reason they went out of business was because that was when neodymium YAG lasers and neodymium YAG pumped dye lasers were just coming onto the market. And so Norm and I went to a meeting at UTRC in East Hartford, Connecticut, and Alan Eckbreth showed us his lab, and he'd just gotten one of these Q-switch neodymium YAG lasers, and he held out a lens and demonstrated that you could break down air. And so Norm decided we needed to buy a YAG laser. He didn't want to get locked into this old technology, and the problem was we only had about half the money, so Norm persuaded the department head, Arthur Lefevre, to give us the rest of the money to buy this neodymium YAG and the dye laser that was pumped by the neodymium YAG laser. And that really set us on a good course because we would have been trapped with obsolete technology just at about the time we had bought the chromatic laser. So instead we got this new commercial system which kept breaking down, and I kept having to take apart the power supply And it was only when I went to Sandia and took an electrical safety training course that I realized how lucky I had been to survive graduate school. So in 1979, there were there's still a lot of things that are unknown about combustion, but looking back on it, we've made a tremendous amount of progress over the last however many years that is, over 30 years. So there was a lot of interest in combustion in 1979 because we had a couple of oil crises. And so the Department of Energy was new then. It was created by Jimmy Carter, and then it was a campaign target at about this time for Ronald Reagan. But when you sent a proposal into the Department of Energy, you had to indicate how many barrels of oil your proposed research would save. The EPA was just starting to crack down on air pollution, and with a tremendous potential impact on the companies were fighting this tooth and nail. They said there's no way we can do this, and it's not possible, and we can't afford it. So, and they've kind of continued to say that, although with less credibility over the years. So laser diagnostics and combustion began in the early 1970s with Raman scattering. I'll talk about what that is. And then it really got a boost with the invention of the tunable dye laser by Ted Hench, who recently got the Nobel Prize for other things, frequency combs and things like that. And so that led to the use of laser-induced fluorescence for flame diagnostics. So that's what I did my PhD on. So in the 1970s, even laminar flame structure was pretty mysterious. This was before we'd started to use lasers to make measurements in flames, and before people were really using computers to model flames. And it's really incredible to look back and see how far we've come in these. And there were a lot of proposals at that time to go in and make measurements in turbulent flames and figure everything out in 5-10 years or so. And so, yeah, it's somewhat like laser fusion in that it's always several years in the future that we're going to figure all these things out. But we understand a lot more about turbulent combustion than we did back in 1979, and that has had a lot of impact. So now in 2015, we're still very concerned about conserving oil and having efficient combustion systems. So we have sort of a bridge maybe to renewables because of fracking technology that's developed. And so, we're not worried about running out of natural gas and oil within the next few decades, like 5 years ago everybody predicted that we would be. But there are other things that, and pollution is still a very important problem. We still want to get NOx and soot down coming out of our engines. So air pollution is certainly much better than it was in parts of the country like Los Angeles than it was in the 1970s and early 1980s, but we still kill a lot of people every year, although it's hard to definitely trace it back to air pollution, but we still kill a lot of people because of things like NOx. And soot also is now being implicated in global climate change. And of course, in combustion, one of the main products of combustion is CO2. So the more efficiently we burn, the less CO2 we produce. So there's still tremendous societal and economic incentives to burn things as efficiently as we can. Laser and detector equipment continues to advance very rapidly. We were making measurements at 10 hertz for like the first 30 years that I was working in the field, and now we're moving rapidly to 10 to 100 kilohertz systems. The other thing that we do multi-laser experiments very commonly these days, whereas back when I started, if you could afford to buy a single laser system, you thought you were pretty lucky, and those laser systems had pretty low power. And so the types of experiments we're doing now, people used to say in papers in the 1970s, if we had another laser system, then we could do these measurements on a single shot. And everybody said, "Oh, you'll never do that." But we do that routinely now. The other thing is that's really helped our experiments is I took my master's data using a chart recorder, and so now we have computers that allow us to control the experimental systems to take data, especially out at Zucro in the combustion lab. We just take a lot of data when we run our gas turbine combustors, pressures and temperatures and everything. And then with these high repetition rate laser systems, we days worth of data taking results in over a terabyte of data. And so it's lucky computer memory has come along and dropped in price so much. So I thought I'd concentrate on femtosecond CARS, but I thought I'd better say a little bit about what Raman scattering is. Raman scattering was really developed or discovered experimentally by one of the most famous Indian physicists in history, Raman. He got the Nobel Prize in physics, where in Raman scattering, a laser beam at a certain frequency goes in, interacts with the molecule, and the molecule doesn't really absorb the photon, but it scatters it instantaneously, and the molecule goes from a ground state to an excited state if you have Stokes scattering. And you can see a little bit of light that comes off of the molecule. It's a very weak process, but that light is coming off as a shifted frequency. And the shifted frequency that it comes off at depends on the molecule. So because it's instantaneous, the intensity doesn't depend on the collisional environment for the molecule. So it's a really great technique, and this was the technique that people were looking at. A number of groups, as soon as the invention of the laser came about in the 1960s and the 1970s, people started to apply Raman diagnostics in the gas phase. Okay, and people tried to apply it in heavily sooting practical combustion systems, because every flame that was practical in the 1970s was pretty much heavily sooting because of the way the combustion systems were configured. The problem is that this is an extremely weak process. Rayleigh scattering, which is scattering at the same frequency, which is the reason the sky is blue, is thousands of times stronger than Raman scattering. So as soon as people tried to apply this to flames that weren't really clean, that had hydrocarbon fragments or soot, even worse, the signal was swamped by interferences. Okay, so Alan Eckbreath, who was showing us that laser, he was developing CARS at that time, said if the Raman scattering cross-section was 100 times greater than it is in nature, then we wouldn't be dealing with any other sorts of laser diagnostics. But it isn't, and so here's a simple diagram for the Raman scattering process, where a laser is focused into a flame, and we collect light from a very small, as small a probe volume as we possibly can, because we want to see what's going on at a particular point in the flame. Okay, and so then that light is collected and imaged and dispersed with a spectrometer and detected with a CCD array or a photomultiplier tube. So the green laser beam is going in, the red laser beam, or the red light, is scattered at the Raman shifted frequency, and the frequency of this red light depends on the molecules that are present in the flow at that point. And the intensity of that light depends on the temperature and the density of the flow. So you can get a lot of information if you can detect the signal above the background, and that's the problem. So CARS was developed. It was first demonstrated by Maker and Terhune at Ford Motor Company. Another difference between research these days and research back in the 1960s was, in the 1960s and 1970s, there were a number of industrial labs that, like Bell Labs, Ford, GM, General Electric, they had a lot of people there and Bell Labs, they just did lots of fundamental basic science. And they don't do very much of that anymore. Everything is sort of funded by the business units. Andy, you were at Bell Labs, right?
A place called Belcorp.
Belcorp.
Bell Labs split up.
Okay. And so, well, anyway, they discovered CARS, and they discovered it actually, I think, in crystals. So the name CARS, Coherent Anti-Stokes Raman Scattering, was assigned 10 years later by a group at Stanford University that, under Bob Bayer. And it was first used as a gas phase diagnostic by Jean-Pierre Tirant at Onur in France in 1973, who detected hydrogen with it, which is a great Raman scatterer. And so in CARS, we have a pump beam and a Stokes beam, and we have 3 laser beams coming in. Here's the pump beam, here's the Stokes beam. And the pump beam and the Stokes beam create a Raman resonance in the medium. And then that Raman resonance scatters the probe beam, and the CARS signal comes off at a signal that is shifted into the blue. And so the advantage of CARS for combustion diagnostics is that we have 3 beams coming in, the signal's coming out at a different frequency, which is good. The species selectivity comes in because we only get a signal when, or only get a significant signal when the pump beam and the Stokes beam here are tuned to a Raman resonance of the molecule. In this case, 2,330 wave numbers is the molecular vibration frequency of nitrogen. And because in this process we have to conserve both photon momentum and photon energy, the signal comes off as a laser beam, okay, because we have to conserve momentum. So in this process we destroy, in this case, a green photon and a yellow photon, and we create a red photon and a blue photon. And so you can, I don't have the phase matching diagram here, but you can only get a CARS signal in a particular direction at a particular frequency. Okay, so that means that you can then take this signal beam coming out as a laser, focus it into a pinhole, and really discriminate against emission from even very harsh sooting flames. Now, we want to make these measurements on the single laser shot. The way we do that is we send in the 3 beams. 2 of those beams, the pump beam and the probe beam, will have very narrow frequencies. And then the 3rd laser beam will be a broadband dye laser. And I'm being very kind to the spectrum here. Actually, it's incredibly noisy spectrally. So in that case, we can detect all of the transitions of the nitrogen molecule at once. This is the fundamental vibrational band, and the little lines you see here are the rotational transitions that are under that vibrational band. And this is what the spectrum looks like at 500 Kelvin, and this is what the spectrum looks like at 2000 Kelvin. And so from the shape of the spectrum, we can determine the temperature in the flow at the point where the beams have crossed. We only get the CARS signal when the beams cross. And so that gives us a spatially resolved measurement. Also, because the beams are 10 nanoseconds, we get time resolution. So this is what a CARS experiment looks like. This is a flame system we still have set up in our laboratory, and it's a hydrogen jet diffusion flame. So it's a simple laboratory flame, or fairly simple as turbulent flames get, that we can use to test out our diagnostic techniques. And what I show here is actually a technique we call triple pump CARS. So we actually have 4 laser beams being focused to a point here, and then the signal is coming off. Unfortunately, you can't see the signal because it's at such a low intensity, at least for nanosecond CARS. That's for femtosecond CARS, we can actually see it. So CARS is an excellent temperature measurement technique. It's non-intrusive. That was a word in the title slide. That means the laser beam's going through here, and it doesn't really affect the flame like if you put a physical probe like a thermocouple in there. If you put a thermocouple in there, the gas molecules would have to flow around it. So the laser does not perturb the flame. The signal comes out as a laser beam in CARS, spatial and temperature resolution. And so CARS is the best temperature measurement technique that we have in combustion, the most widely applied, although it's complicated physically, so there are not that many groups in the world that actually do it. And then there are a number of problems that you have in applying the technique: non-resonant background, collisional line width. The one I'll talk about is that these laser systems that are shown here operate at 10 hertz, so there's no correlation between the laser shots at 10 hertz. in a turbulent flame. By the time you have another laser shot, the flame has changed completely. And the broadband dye laser gives you a tremendous amount of noise on the signal. So to address a lot of those problems, I thought about trying to use femtosecond lasers in the early 2000s. Actually, I was at a Gordon conference and I was listening to a talk by a physical chemist from Heidelberg, I think. And so he had been using CARS to make time average measurements of flame temperature, which wasn't that interesting to me because, you know, you really wanted to make single shot measurements in flames to get at turbulent statistics and things like that. So I figured that you'd never really be able to apply ultrafast lasers to do CARS and flames because the spectrum of an ultrafast laser is just so big. It's an ultrafast laser system with a, say, 100 wave number or 100 femtosecond pulse width is 200 wave numbers wide. And our Raman transitions are, at atmospheric pressure, they're about 0.1 wave numbers wide. So I was sort of half listening to this person, and then I realized that the Raman transition is a two-photon process. And so actually we can excite Raman transitions extremely effectively with these ultrafast laser systems. And then the question is how we can extract temperature and concentration. And I won't go into all of that, but here's why we can couple very efficiently with even very narrow resonances. Say we have a resonant line that's at 2,330 wave numbers and it's very narrow. Well, we can pick out a frequency pair here. This is our Stokes beam and this is our pump beam for the ultrafast laser system. We can pick out that frequency pair and that can be used to excite that transition. But there's another frequency pair that can be used to excite it here and another frequency pair here. So basically the entire bandwidth of the ultrafast laser system can be used to excite a single transition very, very efficiently. And all these frequency pairs contribute coherently to that excitation because the ultrafast laser is actually a single mode laser and has the same phase for this spectrum. And so the other thing we had to do was determine how we could actually make single shot measurements. And the way we do that, this is a theoretical calculation. So we can create a giant Raman coherence in the medium at t = 0 by the interaction of ultrafast pump and Stokes beams. And not only do they excite single transitions very effectively, they excite all of the transitions that we're interested in with the same efficiency pretty much for a molecule like nitrogen. And so at time 0, we get actually a giant Raman coherence in the medium. Now that Raman coherence then decays, and it decays not because the molecules are colliding, but it decays within a few picoseconds. The collisional frequencies in a flame are about 100 picoseconds or so. But it decays because all of those Raman transitions, we excite those with this ultrafast laser pump and Stokes pulse, and they all initially have the same phase. But then they start to oscillate with their transition resonant frequencies, and all those frequencies are a little bit different. And so they start to oscillate out of phase. Now at low temperature, they pretty much all have the same frequency, and so it takes them a long time to oscillate out of phase and for the coherence to decay. At high temperature, though, we have a very large frequency spread of transitions, and so they decay very rapidly. And here you can see some beating that's coming in because we're exciting more than one vibrational mode of the molecule in this case. Well, I could say a lot more about that, but the other thing we had to figure out how to do was how to map the decay of that Raman coherence into the spectrum of the CARS signal beam. And so the way we do that is by sending the probe beam through a rod. So we have this nice, say, 60 femtosecond laser beam here that we've spent over $500,000 to get the technology to produce this pulse at 60 femtoseconds. Then we send it through this rod of glass and disperse those frequencies so that the red frequencies come out first and the blue frequencies come out last. The Stokes beam and the pump beam are nearly Fourier transform limited, so we cross those in the flame. And then we had probed the Raman coherence with this chirped probe pulse, and we mapped the decay of the coherence into the spectrum of our CARS signal beam. Okay, so that is more complicated even than it sounds, and the signals we get out look like this. So when we were first taking this data, we had no idea what this modulation was, because we didn't expect to see modulation, but this is actually the interference of the resonant part of the signal with the non-resonant background. Luckily, the computer was smarter than we were, and the theory is in the dashed red line, and the experiments in the solid black line. And the nice thing about femtosecond CARS is if we take data in a very stable flame, we can get a very, very narrow instrument function. In a turbulent flame, we have vast fluctuations in temperature, and so in a pseudo-laminar flame that we were developing the technique in, we're measuring pretty much always the same temperature, 1592 plus or minus 10 Kelvin in this case. So we had been developing this technique for quite a few years, and so then we decided to try some measurements with researchers from DLR Stuttgart in a swirl stabilized burner. And Claire Dennis and Carson Slabaugh are in the audience here. And so this is the burner in operation. And you can hear it a little bit here. You can barely hear yourself think in the lab when this flame is on. In fact, one day I'd forgotten my key card for the lab, and I tried to get into the lab and they couldn't hear me. So we, despite the very, very high levels of turbulence in that burner, we were able to make temperature measurements on almost every laser shot. So here's a velocity field diagram of that flame. And so here we have a recirculation zone point where we expect the temperature to be pretty much stable, and that's what we observe. And then here we are in the shear layer where the fuel and air are mixing, and so we have the shear layer moving back and forth and lots of turbulent interaction going on. And there we see a much greater spread of temperature measurements. So we're continuing to work on this technique, and eventually we'll want to apply it in high pressure turbulent combustion. And so we've done things like use a dual detection system to increase the dynamic range. So I'll sort of skip over that. But we are able to make measurements at 5 kilohertz in these turbulent flames. And one of the challenges we face is that the temperature in the flame can go from 300 K to 2400 K, and the signal level drops by a factor of 1,000 when that happens. Now the measurements were performed in this highly turbulent swirl stabilized flame from DLR Stuttgart. So they wanted to learn how to use femtosecond CARS, and we wanted to learn how to do high speed particle imaging velocimetry. So that's what I'll turn to now. I'll talk about our measurements in high pressure combustors. And these are measurements we're making out of the Zucrow laboratory. And eventually we want to apply things like femtosecond CARS in these systems. But I'll talk about the measurements we're making now. And so in particular, I'll be concentrating on the aviation gas turbine testing or experiments that we're doing. Okay, so why do we want to make measurements in high pressure combustion systems? Well, we're trying to help the gas turbine industry in this country. So these systems are very complex. The combustion changes considerably as the pressure increases, so you can't do atmospheric pressure measurements and figure out what's going on in these high pressure systems. And gas turbines are still something the US makes that the rest of the world wants to buy. And a lot of the research in at least civil aviation is directed at trying to get very, very low pollutant emissions. So this is actually a military gas turbine. This is the engine for the F-22, and so the combustor is right here. It's kind of hard to see, The volume that the combustor actually occupies for the whole engine is surprisingly small, but there's tremendous energy release in that combustion zone due to the very high turbulence levels, and that's what keeps the airplanes in the air. All of this is the compressor, and then there's a little bit of a turbine here in this aircraft engine, and then here is the afterburner. So for not so much for military, but for aviation gas turbines, what we want to do is we want to minimize the amount of pollution that we produce from burning the fuel in the air here. The compressor produces high pressure air that's heated to a very high temperature also. The fuel is sprayed in, and it used to be that the fuel was sprayed in with a nozzle that would mix the fuel very far from the nozzle. And so there would be lots of regions where you would have too much fuel for all the air to burn. And that would produce a lot of smoke and nitric oxide. And so now the approach is to try to burn as lean as you possibly can to try to premix the fuel and air before the combustion process starts. And that way you avoid creating soot because you don't have too much fuel for the air to burn. And you also decrease the nitric oxide because the nitric oxide doesn't really form if you can keep the temperature below 1800 Kelvin or so. Now the problem is, as you try to burn leaner and leaner, the flame becomes less stable. You have combustion instabilities, and you have to be very careful about how you do it, because if you just premix the fuel and air, and it would flash back and start burning up your aviation hardware. So we have an aviation gas turbine combustion test rig that we've been developing out at Zucrow. Really, it started under 21st Century funding and then NASA funding. And about 4 years ago, General Electric Aviation started to fund us to look at their advanced lean premix pre-vaporized injector, which we're not supposed to say the name of it. But this is a test rig that Carson Slaybaugh and others have been working on, and we've demonstrated operation at 1.5 megawatts of thermal energy release in about a liter volume at pressures above 20 bars and with inlet temperatures up to 760 Kelvin. So that'll be going up in the near future. So this is a video of. We use a laser to ignite the flame. That's the little flashing you saw there. And the reason we do that is we use a lot of nitrogen to film cool the windows. And so it used to be to ignite the burner, we had a spark plug in one of the, and we replaced one of the windows with metal. We had a spark plug, and so we had to flow a lot of fuel in order to get the stoichiometric mixture right at that spark plug. Also, we had to turn the nitrogen off. So once we had a flame ignited, then it was a panic to try to get the flame turned down before we burned up the test rig. So laser ignition really helps us in terms of rig safety. So I'll just show that one more time. So this is the flow is coming in. This is the main flow. There's actually no fuel coming in the main. This is called a heat shield. That's what's turning purple there and heating up. And so this is all pilot fuel at the moment. So this is a very, very clean burning flame. You don't see a lot of soot there. It looks very blue in the laboratory, and that is because it's really being premixed and leaned out before the combustion starts. So we don't produce soot that coats the windows at all in this burner. Okay, that was a low-speed video, which surprisingly the people at GE really like to look at. That was just a GoPro video. And so this is a video produced of the combustion zone by a high-speed camera operating at 5 kilohertz. So the flame looks really, really steady with the GoPro camera, but actually there are a tremendous amount of dynamics going on there. And in particular, the flow is coming in and recirculating back. The fuel is coming in, recirculating back and burning in what's called the recirculation bubble. And that's what we're most interested in looking at for General Electric. So this is just a little bit on the design, and Carson Slaybaugh was the principal person who was working on the design here. Scott Meyer, who's also here, was also involved in that early process where we spent about 6 months talking about this design with GE. And one of the reasons our windows survive so well is we use high pressure nitrogen to flow over the window. And we have a lot of nitrogen out at Zucrow, and so that was an idea Carson had. And so we get a nice film cooling of that window, and it survives even though a lot of times we think the flame is impacting actually right on the window. So here's a photograph of the system in operation, and then it looks completely green here because we're using a green laser to do particle imaging velocimetry in the system. So, we got the green laser that we're using is called the PIV laser. It's a dual head system. It puts out a beam at 532 nanometers in the green and really gives us some spectacular pictures. And the way we operate is we form a laser sheet. The beam comes out, and we use cylindrical lenses to focus it in one dimension and to spread it out and collimate it in another dimension. So we get a sheet of light coming through the chamber, and the PIV laser puts out two very close, two laser pulses that are very close in time. And so we look at we seed titanium dioxide particles into the flow, and then we look at the scattering with the PIV camera from those particles, and we see how they move from one image to the next image. And from that way, we're able to determine the velocity in the flow. Now, we also use another laser, and this laser doesn't give us very good pictures at all because this is a 283 nanometer beam that we can't see. But this 283 nanometer beam is tuned to a resonance of the OH molecule. And so that tells us where the flame is burning. So from the PIV measurements, we seed particles in, and we take two very rapid snapshots, and that tells us what the flow velocity is in this plane. And then the PLIF sheet is overlapped, and that tells us where the flame is burning in this sheet. Okay, so we're trying to look at the influence of the velocity field on the reaction fronts. So here is scattering from those particles. This is a PIV image when we don't have any liquid fuel injection. And so we take two of these images like this, spaced by 8 microseconds or so, depending on what we think the flow velocity is. And then we can track the particles using some sophisticated algorithms and determine what the velocity is at a point in the flow. Now, in these high-pressure systems that are liquid-fueled, we have a lot of droplets coming in, fuel droplets coming in. So this is a picture with no PIV seed. And then here's a picture with the droplets and the PIV seed. So we have to figure out how to discriminate against the liquid droplets or maybe use that information. The other thing that happens as we start to go to higher and higher pressure and thermal heat release is we start to get blurring in the images. And so we're fighting a lot of those images, or a lot of those issues as we go to higher and higher pressure. Okay, but we've learned how to deal with a number of those. So here's a movie that just shows the velocity field in this General Electric injector. And so this is referred to as the main, and this is the pilot. This is the pilot airstream. This is the pilot fuel. This is the main fuel, and this is the main airstream. So we get very high velocity air coming in here and also in here, although the pilot airflow is not nearly as high velocity or momentum flux. And then we get a recirculation bubble here. And so we have a wide dynamic range of velocities in this flow that we have to be able to handle with our particle imaging velocimetry measurements. And I think if you saw that, you could see a significant vortical structure. You can see that the flow has some vortical structure in here. And so we see a lot of interesting things looking at these measurements. So we combine that with the OHPLIF, and so all of these measurements are made possible by the introduction of these diode pumped solid state lasers commercially about a little less than a decade ago. So we do the same thing with the OHPLIF. Here's a laser sheet coming in, and here it's a grayscale image, so the high intensity regions are where we have a lot of OH. And you can see here we don't have reaction, and here we have reaction. This is the pilot region, and here we have a region where the pilot and the main are reacting, are interacting. And then here we have the heat shield region, which is a region of interest where we're getting reactants right on that heat shield, which I think I'll just kind of skip over how we process the images here. And this is the system in operation. And so this is one of the way we process the images is that we use flame edge detection, and so we get flame surface density out of the OH measurements. So here is the time average flow field where we take those instantaneous measurements and we get the time average flow field, and we can see some structure here in the heat shield region here, where we have some recirculation zones. And then if we look at the OHPLIF measurements, we actually get a significant amount of flame surface density right here at the edge of the heat shield. Okay, and then we get a lot of reaction here also. Most of the main fuel goes out with the airflow here and then comes back and recirculates and burns in the recirculation bubble. So we were operating I shouldn't say we, Carson and Andrew Pratt, and I believe, and maybe some other people were operating the test rig one weekend trying to get up to 300 PSI, and they called me I was at the movie theater, and they said, we cracked the heat shield. And so I thought, oh, that sounds bad. And so, well, we talked to General Electric. That turned out to be a common failure mode for this particular injector. So they were actually quite interested in that, just said, oh, just keep monitoring it. So we continue and have continued to operate for many years with that cracked heat shield. But and now with the PLIF and PIV, we can see why we got that cracked heat shield. So we've developed this test rig, and really over the last 4 or 5 years, we've really demonstrated how to have windows survive and make measurements both in this test rig and in another test rig that other test rigs that we have for power generating gas turbines. And so we can make measurements up to 17 bars now that we've demonstrated. General Electric wants us to go up to 40 bars. And we've developed a lot of analysis tools for extracting quantitative information from the measurements. So what we did with that test rig, like I said, General Electric wants us to go up to 40 bars. And so this is the test rig that we designed last year and is being fabricated right now. And so this test rig, it's everything you see here pretty much here is Hastelloy. And so this test rig turned out to be a lot more expensive than we had anticipated at the moment. It's a lot bigger. These windows are 3.5 inches thick, and so this is basically 2 feet in diameter. And so with this test rig, we'll go to even higher thermal energy release rates, and we'll go to 40 bar. So we've been designing that, and now that is being fabricated, and in the next couple of months, we're going to have to put it together and run it. So other things that the group has been working on is the flows we are looking at are highly swirled, and so we really want to get at that third component of velocity. Right now we're doing planar measurements, but we're only getting the velocity that's in the plane of the laser sheet. If we have a couple of cameras that are looking at that laser sheet at angles, then we can use triangulation basically to get the third component of velocity. So this is something that people do pretty routinely in atmospheric pressure flames and flow systems where you don't have windows to deal with. But again, Carson went over to DLR Stuttgart last year to learn how to do stereo PIV and high pressure flame systems. And so now we're doing that out in our test rig at Zucrow. So these are some of the images from the stereoscopic cameras and then a reference camera. And so there are a lot of sophisticated algorithms for we're trying to reduce error in these measurements that are Carson and Pavlos Vaklos are working very closely on this, or on algorithm development, or at least we're consulting with Pavlos to try to make sure we're getting the most accurate measurements we can for the velocity field. So as soon as we started to take measurements at 10 kilohertz, we realized, and probably we realized this before also, but it was really kind of depressing when we would take measurements 5 kilohertz. There's actually very little correlation between the images when we're in this very turbulent, very highly swirled flow. And so we really want to move towards 50 kilohertz, and there are a couple of ways of doing that. We have ordered and have now delivered a 150 watt edge wave pump laser that can go up to 40 kilohertz. And we're doing these, Sarah Eisert is doing measurements with Kevin Cho on propellant combustions. We got this laser, Steve Sun and I wrote a proposal to the Army, or to AFOSR to do propellant research. The cameras have to be able to take data at that higher rate, and so the cameras we're working with now pretty much max out at 5 kilohertz for full resolution. So our cameras we have are 3 or 4 years old. So we need to get higher, more state-of-the-art cameras that they continue to go higher and higher frame rates for more and more pixels. And then the other thing that we're doing is we're buying a pulse burst laser that'll allow us to get to over 100 kilohertz. These lasers operate at overall repetition rates of much less than a hertz, but every time they have they have a burst of pulses that lasts from 1 to 10 milliseconds, and so we can get 10 to 1,000 laser shots out at frequencies of, say, 100 kilohertz up to 1 megahertz. So this is what our DPSS laser systems are doing right now. We have pulse spacing of 20 to 200 microseconds, and those just keep lasing as long as we keep the systems turned on. But with pulse burst laser system, we can zero in and really make very, very high repetition rate measurements at a particular time in the flow, and hopefully our flow is statistically steady enough that our statistics will converge over, say, 1 to 10 milliseconds. That's not evident that that is the case. We also want to extend the femtosecond CARS from a point measurement to a line measurement, and we can do that by focusing our beams instead of with spherical lens that focus them to a point, focusing them to a line. And so Claire Dennis is actually back from China Lake this week mostly struggling with the laser, but this is the experiment we're trying to do at the moment, using 2 beams, pure rotational CARS experiment. And what we would like to be able to do is take line images and make temperature measurements along a line in our gas turbine flow at data rates of 5 to 10 kilohertz. So to do that, we actually need a new building, which was just fully funded. Out at Zucrow, our laser lab right now is about 150 square feet, and it has a window air conditioner in it. And so the ultra-fast laser system wouldn't even laze in that type of a room. So there was an announcement about in mid-February, and I'd like to thank all the people that were involved: Steve Heaster and Anil Bajaj, Tom Shee, the dean, up through the president, that were involved in getting funding for this building in place. So we'll have a building where we have 5 test cells now, each are as big as the test cell we have right now that has about 5 test rigs in it. So the graduate students I hire now have to be pretty much contortionists in order to work in that test cell. So we'll have 5 test cells, and then we'll have a 2,000 square foot laser laboratory that runs along the length of the test cells. And that laser lab will be suitable for running things like the ultra-fast laser system. And so we'll have combustion test rigs in there, and there will be a turbine heat transfer test rig in there. And I think almost as soon as this building opens, we'll probably fill up those test cells. Groundbreaking is now scheduled for the spring of 2016. And we are putting in a new air heater, which will allow us to go to 1,500 degrees Fahrenheit instead of the present 1,000 degrees Fahrenheit. And this is something General Electric really wants. The modern compressors for aviation gas turbines have very high pressure ratios, and so the gas coming out of the compressor going into the combustor is at about 1,500 Fahrenheit. And I know Rolls-Royce is talking about even higher temperatures. And so our current air heater, which is probably 40 years old at least, Scott Meyer knows for sure, is about 1,000 degrees Fahrenheit. And so this also will have much better control, and it has 850 psi maximum operating pressure. And this was funded by the OVPR, and this is about a $2 million air heater. So I hesitate to put this slide up because I'm sure I left some people out. And these are just the people I want to thank for the high repetition rate measurements and high pressure test rigs. And I've really only talked about 2 aspects of my program, but I would like to thank all of the graduate students. Jay Gore and Bill Anderson are faculty members I've worked with on the high pressure test rigs, Scott Meyer, and then the people who have funded the work out at Zucrow, starting with the Indiana 21st Century Fund, and then leading on to working with GE Aviation, Siemens, and Rolls-Royce. And one thing about working with industry is they said in Ghostbusters, they expect results. So it can be pretty high pressure. So with that, if you have any questions, I'd be happy to answer those.
Bob, when you're saying for the gas turbine combustor, the pressure will go from 17 bar to about 40 bar. And for laser diagnostics, especially high frequency PIV and PLIV, what would be the challenges when you go to 40 bar?
Oh, well, the main challenge will be that as you go to 40 bar especially in the combustion zone, the refractive index gradients are going to be very severe. So we can really see that at the images I showed there. I think we're at 17 bar or close to it. So the particles start to blur. And so that's something that Carson and Pavlos are very, very interested in, I think. I can say that. And so it's going to have to be dealt with via algorithms, and maybe making measurements with multiple cameras so that you have a better estimate of where that particle actually is on each laser shot. Now, luckily, they're interested, at least at first, not in the combustion zone, but downstream of the combustion zone, where the refractive index gradients are going to be much less severe. The other thing we face in making these kinds of measurements is that we can't make measurements for very long, because either the particles get soft and stick to the windows, or the windows get soft and the particles then stick. But the particles eventually coat the windows, so we have a limited time that we can take data, which is another reason we have to have the high repetition rate laser systems in order to do these measurements.
Bob, you have developed methodology for making local instantaneous measurements of temperature. I would like you to develop methodology to measure temperature distribution, instantaneous temperature distribution. What are the challenges?
You sound just like General Electric. Well, the challenge is that we're trying to move towards that by doing line imaging of temperature measurements. With cars, there has been a demonstration that you can make planar measurements at low repetition rate. And so the challenge is the signal level as you go from a point to a line image, for example. And then also extracting the data, and so the challenge is basically signal level. Now there are other types of proposed methods for making temperature measurements in a plane, for example, like two-laser PLIF, but I don't believe in those types of measurements because they're too susceptible to very large systematic errors due to things like laser absorption and fluorescence trapping. Now, something we're also looking at is another potential method is by using a technique called filtered Rayleigh scattering, which we may try to do that. That would probably be a very good technique for the downstream region of our combustor at 40 atmospheres. So there are techniques. They're very complicated. And so we've spent most of our time in terms of the gas turbine for the last 5 years working with techniques that we know they're going to work. And the simultaneous PIV and PLIF give us a lot of information that we're still trying to figure out how to work with the data that we have there and how to give it to the companies in ways that give them insight. But yeah, everybody would really like a volumetric temperature measurement, and they want it at 100 kilohertz also. But we're moving towards that, I think.
Thank you.
You've shown, I think it was slide 10, the signature of the rotational modes, or rotational energy.
Yeah. Mm-hmm.
So, is there how challenging would it be to apply the same technique in the case of non-thermodynamic equilibrium, where you have multiple temperatures? And is Raman scattering, but I don't know much about it, but is that based on the assumption of thermodynamic equilibrium of the gas?
No, in fact, some of the early measurements, especially in Tehran's group, were performed in highly non-equilibrium plasmas. And so in combustion, we almost always make the assumption that we have the same rotational and vibrational temperatures. But we have information on both the vibrational distribution and rotational distribution in the spectrum. We just have to figure out the correct way to analyze it if we're in a situation where we don't have that thermodynamic equilibrium. But they have some spectra where they have multiple vibrational bands that are very, very rotationally cold that I've seen before.
So this could be applied in very high-speed flows. Have people taken measurements in hypersonic?
Yeah. Yeah, again, the French have done that. It's very difficult because the problem with high-speed flows is not the non-equilibrium, it's the very low density. And so,
Don't have enough molecules.
yeah, so CARS is a technique where the signal intensity is basically proportional to the density squared. So in the gas turbine combustors, that's really going to help us. But in hypersonic flows, it's a problem. You live and die by number density squared, basically. So it's great when it's increasing, but your signal really falls off when it's decreasing.
Interesting. Thank you.
Any other questions? Yeah.
You got lots of grad students in here. Can you offer how your golf handicap correlates with your career success?
Yeah. Well, I played golf once last year, so, and you know how that went. So, I can only play scrambles at this point. So, but yeah. So, my daughters keep me pretty busy also. So I will say so. Yeah. Yeah. When I got tenure, I thought I was going to have a lot of time to play golf, but things just keep getting busier and busier. Yeah. Oh, well, I got tenure at Illinois, so that was a long time ago. So.
That's why he kept moving.
Yeah.
Getting new challenges.
Yeah.
Any other questions? Okay, let's thank Bob.